Okay, we should be streaming right now. Let me check. Yep, we are now live. So welcome. Welcome everyone to the second session on relativity. We were talking about special relativity on the first session, and so this is going to be session 2, and this was our first session, if you remember. So I'm going to sort of zoom out a little bit so that you can see more of the area within the screen. So in the last session, we talked about relativity, specifically special relativity part of it, and for now that is the goal, to explore that segment of relativity. I think if I can finish it, then I'll be able to go on to the second session, which would be the general relativity, which is, I guarantee you, is more interesting, more fun, more mathematically involved though, but I will try to boil it down to the easiest version of it, and that's the goal of these live streaming sessions. So excuse me. So we have relativity. Relativity did not start with Einstein. It actually was well presented in Newtonian mechanics, which is called the Galilean relativity. And after Einstein, we had something else which is called the Minkowskian relativity. So that's a bit different. And they have shared characteristic. Specifically, one of the tenets that is used by Einstein as a postulate of Minkowskian relativity or Einsteinian relativity is actually borrowed from Galilean relativity itself, which is basically the principle of relativity we talked about in the last class. So we'll see that in a moment. We talked about how we have to use to describe any physical event. We need to use 4 numbers, not just the spatial location, but also at which time it happened. So since we live in 3 spatial dimension, and if you add time into the fold, then you need 4 numbers. But we don't say at least in Galilean relativity in mechanics, we didn't say we live in 4-dimensional worlds, because we didn't treat the spatial and temporal coordinates in the same regard. Okay. But we have the clues. If you have done electromagnetism or a lot of ideas in classical mechanics involves both space and time, and so there was clues, but time flowed independently in classical mechanics, and so time and space are sort of independent of each other. So you can think of the Galilean relativistic world as sort of a collection of snapshots stacked on top of each other, which could be called space-time, but that's not amalgamated, that's not joined together. It is a conjoint world. So in Galilean world we had space hyphen time, so they are separated. They're both together, but they're still separated. In Minkowskian relativity, as we will see, they are brought together because they are treated in the same fashion. So we don't put the hyphen. So space-time becomes one whole thing. So that is like a stark difference between the Galilean relativity and Minkowskian relativity. Okay. Usually the thing that we start with is something called an inertial frame. So there are reference frames. So what's the reference frame? It's basically 3 coordinate axes, right? 3 scales, if we might call it that. The axes are akin to scales, and these scales, these axes, help us to locate any point in the space with just 3 numbers. Okay, but also, since time comes into the fold, so we need also a stopwatch or a clock, okay, so that we can determine the 4 numbers that are required to specify an event or location in space-time. Okay, so that's basically a reference frame. The 3 axes, they intersect each other at a point which we call the origin. At the origin, or at each point in the coordinate axis, we have a synchronized clock, but we don't need that because we don't need that in Galilean relativity, because the time flows independently. But as we'll see in Einsteinian relativity or Minkowskian relativity, the clock has to be attached at each point, right, in a specific synchronous manner, so that when you have taken one clock from one position to another, you took it very slowly, so that there is no relativistic delay or effect that has been induced into the clocks when they have been transferred, and everything is synchronized. So the idea of reference frame differs a little bit in Galilean and Einsteinian or Minkowskian space-time, but the idea is sort of the same. Okay, you can construct both in the same way, but in case of Galilean relativity, the clocks don't differ. They are synchronized by nature because time is independent, if you know what I mean. So that is the inertial frame. And then we argued for acceleration should be 0. If the acceleration is 0 in a frame, then you should be able to look at physics in a certain way, which we call the inertial frame. So in what way? So we know that acceleration is physically detectable, right? If you're moving in a train that is not accelerating, you won't be able to determine its speed, right? Whether it's going 100 miles per hour or 1 mile per hour, inside the train, as long as the train is moving at a constant velocity, the nature of the physics is going to be the same. So you cannot make an experiment to differentiate between the 2 frames. And as soon as you introduce acceleration, then immediately everyone recognizes the acceleration. Every inertial frame recognizes the acceleration, and they can measure it correctly. Okay, so the inertial frame is a frame, a reference frame where the acceleration is 0. Okay, and so here we describe an experiment which you can do. So as soon as if the train is going at a constant speed, there is a pendulum hanging from the roof that doesn't swing, but as soon as it starts to accelerate, then it starts swinging. Okay, it starts moving, and that's how you can determine its acceleration, and that's something that every observer will be agreeing upon. Everybody will see that the pendulum is swinging, so they will be determining the acceleration, and they will be correctly able to determine the magnitude of the acceleration. Okay, but if it's a inertial reference frame, then there's no way to differentiate between the 2. Okay, only what we can agree between 2 inertial frames, if one can see the other, is that there is relative motion. But which one is actually moving and which one is probably sitting down, you cannot differentiate between the 2. Okay, unless you can somehow physically see that as well. So since there exists a class of preferred non-accelerating reference frames, these are the places where Newton's first law holds. Okay, And if the Newton's first law hold in any reference frame, then we call it inertial frame. Okay. So saying that something is non-accelerating is equivalent of saying that this is the place where Newton's first law holds. And Newton's first law basically says that without any external force, the velocity basically remains constant. So that can change if you're accelerating. So as long as you're not accelerating, then it's an inertial frame, because it's the frame where Newton's first law holds. And we talked about what's the meaning of that, because A is a vector, acceleration is a vector, it has 3 components, at least in Cartesian coordinate. And so acceleration becoming 0 requires that each of these independent coordinates has to be 0 separately. So without gravity, 2 inertial frames can differ from each other only by 3 means. One is a translation. Translation means a certain gap, right? A rotation, that's also not, it doesn't mean it keeps rotating, that would be inducing acceleration. It means a frame that is already rotated, or a frame that is already translated, or a frame that is at constant velocity with respect to other. Okay, so these are only the 3 ways the 2 frames can differ from each other. Okay. So the principle of relativity, if we have an inertial frame, the principle of relativity says that the laws of physics take the same form in every inertial frame. That is the principle of relativity, and that's our starting point. Okay, so once again, we start from the principle of relativity. Is that principle? Yeah, I think we're correct in spelling. Principle of relativity. Okay, so this is also called the law of covariance. Okay, so as long as you are in inertial frame, in all inertial frames, in all inertial frames, the laws of physics looks the same. Okay, so and it applies in both Newtonian theory and special relativity. So this is applicable in both Newtonian relativity and special relativity. Okay, so the Newtonian relativity and special relativity is so far the same in this principle, but where do they start to differ? That's the question, right? So what we are going to do, we're going to use 2 frames, and we'll be inspecting or scrutinizing where they start to differ. So what we are going to do, we're going to build 2 frames, and we could do that arbitrarily, right? But that is actually complicated, and that defies the necessity of introducing an additional complexity that is not really required. Okay. What we are going to do is this. So there is a frame. Let's say so there's an arrow. Okay. So there's a arrow in this direction. Can I make it a bit straighter? Yeah, this looks straight. And I'm gonna define another arrow in this direction. Okay. And there are two other directions. So should I draw another one? I think I should. So let's say from here I draw another one in this direction. So this is a bit out of the place. Let me see if I can put it back to where it should be. Okay, great. So I'm going to take a copy of this and make a copy, right? Paste it here. I'm sorry. So copy. Yep. I'm probably make it a different color. What color should I choose? Let me choose how about this? Okay, not bad. Okay, so we have two frames and one of them is moving, right? And let's call this one this axis as X, this as Y, this as Z, and similarly X prime, Y prime, Z prime. I'm sorry, this should be Z prime, and Y prime. So they are sort of analogous except for the fact that one is moving with respect to the other, and we sort of signify that like here, right? The one is having a velocity. What would be the velocity? Let us call this velocity v. There's a vector, but it's in the x direction, so we'll be just writing v times x hat. So it suffices for us to just denote the velocity by v without the arrow, because we know the direction and we know the magnitude. And so one is a prime coordinate, one is the unprimed coordinate. The unprimed coordinate will be denoting by s, the primed coordinate will be denoting by s prime, and this is the standard configuration. Okay, this is the standard configuration. The motion is in the x direction, so if we do have any relativistic effects, then it should be in the x direction only. And the argument for that is nothing is happening in the z and y direction. Okay, we'll be going even further. So what we're going to do is this. So we have the time as well, by the way. So there's a clock. So this one has time t, and this one will be having a time t prime. And also in addition, at when the time started, which is at t equals t prime equals 0, when the time was 0 in both clocks, then these two frames coincided. The two frames coincided. So there is no initial separation at the beginning. So of course the s prime was moving, but right when let's say the time went from -1, -10, -9, -8, and so on and so forth. Or it doesn't have to be. I mean, negative time is something that probably isn't very comfortable. It's just a time-keeping device. So let's say the s was sitting here, and s prime comes here, reaches in this position where the two origins coincide. At that time, both of these clocks are started. That's what I mean. Okay. Once you do that, if there is no initial separation, then you can make a relationship between these two coordinates, and the relationship should be simple and let's say linear. Okay, it ought to be, and the relationship is something like this: t prime equals a times t plus b times x. Now you can say, okay, why not c times y and then d times z, and then there is a constant. Well, first of all, the constant is not there because precisely because of this condition, right? When t equal to t prime equal to 0, then x equal to x prime, and y equal to y prime, and z equal to z prime, and the zeros of all of them actually coincided, so therefore there is no extra constant. And because there is nothing happening in y and z direction, it's not likely that those two will influence the time itself, or even x. And by the way, x, y and z are themselves independent of each other to begin with, so this is the this is going to be the correct answers. Okay, then we can do more. We can, with a similar argument, do write a relation for x prime in terms of t, x, y, z, and that is going to be some constant d times t plus e times x. And this is for the previous reason that we have just cited. The motion is exclusively along the x direction, so if something influences time, it's going to be x, and every value of y and z is equal to the correspondingly y and z prime. So they are sort of separated and they don't come to play. So y prime equals y and z primes equals z, and that is by construction. Okay, so this is basically the linear transformation that designates the standard configuration. Okay, now if after some time has passed, okay, so after, let's say after some time, let's say t time has passed in the clock of the unprimed coordinate, then there is a distance, right, between the two. So after t time, let's say what should I draw? Okay, use a different color. So after t time, from here to here, we ought to have the relation. What the relation should be? It should be x equals vt. Okay, so what is that point? It is this point, right, where x prime equal to 0 would correspond to x equals vt. Okay, so if x prime equal to 0, x equals vt. Well, then the question is, where is this point? Okay, x equal to 0 in terms of the coordinate of s prime or x prime, and that would correspond to x prime equals minus vt prime. Alright, so everybody is using their own clock and own yardstick to measure where the other observer or other coordinate origin is, and this ought to be the relationship. Okay, so after t time has passed, the x equal to 0 point has moved to x equal to vt, and because this is moving in the forward direction, he will observe that the what should I say, the origin of the s is moving in the opposite direction. So in his frame, x equal to 0 would correspond to x prime equals minus vt prime. So let me, yeah, so this is what should we say, x equals vt, okay, and x, this distance x prime equal to minus vt prime, okay. So if I say good, so then after some time I'll have this, x prime equal to 0 would correspond to x equals vt, and x equals 0 would correspond to x prime equals minus vt prime. Okay, so if we try to substitute that in here, what do we get? So let me just move them a little bit. Okay, just copy it, right? Let's just copy it, go to the next page and paste it like here. Let's make them a bit smaller so that we can do some side calculation. What do we get, right? Important question. So this gives us, what does that give us? So x prime equal to 0, okay. X prime, if the x prime is equal to 0, which is equal to d, which is also equal to, not implication sign, dt plus ex, but ex is basically e times vt. Okay, so we can, what can we do? We can take d, so from here we can imply that d equals minus e times v. Okay, okay, then say x is equal to 0. What does that mean? If x is equal to 0 and x prime equal to minus vt, so instead of, so I'm taking this relation again, so what I'm saying is x prime equals minus vt prime equals d, and then well, t is there, you cannot do anything, but x is equal to 0, right? X is equal to 0, that was the condition. So what do we get? Okay, that's, but also from here I get t prime equals a times t plus b times 0, so that's what I get, right? Now from these two, can we make any deduction? Yes, we can. So basically divide one by the other, so you have minus v t prime divided by t prime, so they cancel. I have d divided by a, so from here I get d equals minus av. Well, hold on a second, d equal to minus ev and d equal to minus av. Okay, great, because that means a equal to e. Okay, so a is equal to e, and they are, each of them is equal to minus d divided by v. Wonderful, wonderful. Now let's substitute that in this relation. So if a is equal to e, let us skip the a and let us keep b and substitute e and d. Okay, so what do we get? What do we get? We get this. So from here I get t prime equals at plus bx. Okay, notice I haven't really applied anything. This is still general, and this is applicable to both Newtonian and Einsteinian mechanics. So t prime, and what do we have? X prime equals, so instead of d, I'm gonna do what? So let's do a little side calculation, shall we? So we can do it here, I think. So instead of d, I can write minus a times v times t. Okay, instead of e, I can write a x. So what does that become? That becomes x prime equals a times x minus vt. Okay, and from here I get t prime equals at plus bx, and of course y prime equals y and z prime is equal to z. So y prime equals y and z prime equal to z. From the next time, let's just ignore the last two relations because they are sort of trivial and nothing interesting is happening there. So we'll just be talking about the first two relations, these two here. Okay, does that make sense? So we'll give it a number. Let's see if I have given any equation any number yet. No, I don't think I have. So the first thing I want to do is to give this one a number. So 1. Anything else? So yep, this also a number. So let's just 2. Okay, so this is equation number 2, and this is still general. There is nothing wrong with it. And now we'll be applying different conditions. So what are the conditions? If you're talking about Newtonian geometry, okay, so let's use a different color. So Newton's geometry, Newton's geometry. Newton's geometry, we know that space and time are separate. Okay, so what does that tell us? So first of all, there has to be an assumption. The first assumption in Newtonian geometry is that the time is universal. So that would mean that whatever s is measuring is the same as s prime is measuring, and both times are the same. Okay, so that is our that is our assumption. Okay, that is our assumption. I don't have to write like number 1. Okay, so time is universal in Newtonian space-time. So what does that entail in? So from 2, it gives us, what does it give us? It gives us, so if t is equal to t prime, okay, if t is equal to t prime, then in this relation we notice that b is 0, this is 0, and this is 1. Okay, so that's what we're going to plug in. So that would mean b is 0 and a is 1. Okay, so once we have that, then the relation becomes, what does it become? It becomes a t prime equals t, and x prime equals x minus vt, and y prime equals y, and z prime equals z. And you can have the inverse relation of this. So I'm sorry, this should be t. Okay, you can have the inverse relationship. So the inverse relation is, what is the inverse relation? So it's basically the replacement, because of the symmetry. everything that has v should be replaced by negative v. Okay, so that would entail in t prime equals t, so that doesn't change. I'm writing it the other way around. T equals t prime. Okay, then I have x equals x prime plus vt prime, and then y equals y prime and z equals z prime. So we have these two relationships. Okay. I hope this is clear to everyone. I hope there is no confusion here. Okay. There is a background sound. Okay. I hope I had a better sound system. Okay, let me see if I can reduce the sound using the fan. Okay, this should be a little bit better, but I'm not sure that it is going to do any magic good. Excuse my sound system. This is I understand what you're saying. This is a bit difficult right now because I only have one microphone. So again, apologies. Don't worry, I'll be posting this in my channel as well after I have finished the live streaming. But notice what we have found. This is our familiar relationship, right? So I'm gonna draw a sort of rectangle. So let's first put it in place. Okay. Now let's draw a rectangle around this so it looks better, like that. Okay. So notice the space and time, they are separate. They are clearly valid. This is something that we already know from Newtonian mechanics. This is valid for any two inertial frames S and S prime. That shows that the time coordinate of an event P is the same in all inertial frames, number one. And the number two is basically the common sense equation that we know leads us to the addition of velocities. And this is actually the very important part, even though it looks trivial. So if you have if you have x prime equals x minus vt, you can differentiate that with respect to the time t. So dx prime dt, but that is nothing but dx prime dt prime. Okay, and that is what? That is v prime. But on the on the right hand side, I have dx I'm sorry, I should call this actually u prime, right? Because there is a v here, so I cannot write v in two places. So let's call this u prime. And we have here dx dt minus v times dt, which is 1. But dx dt then should be written as u minus v. So notice what we have found here is very interesting, is that we have found the velocity addition formula, v minus u minus v, or u equals u prime plus v. Okay, so this is what we call the velocity addition formula. Okay, so velocity addition formula. Okay. so that's great, and from that we can right now find out that the acceleration are actually the same in both cases. Okay, so from here you can show that acceleration is the same in both frame because you can now differentiate it once again with respect to the time. So du prime dt, which is going to be which is going to be du prime dt prime over dt prime. I'm sorry if you're a mathematician, please don't be angry with this, because this is not a fraction, but that's how I'm dealing it with, because it behaves like a fraction. So this is going to be a prime. Okay, in fact I should probably put an x here, right? ux and then ux here, because the velocity is in the x direction. So but this is fine, actually. This is fine. So ux, so this is ax. Okay, what's on the other side? So I have d dt acting on u minus v. But notice v is a constant, right? V is not a number, so its time derivative is 0. But then du dt, that is just a. So what have we found? We have found the acceleration in both frame is measured to be the same. Okay, if there is acceleration of a particle going in one frame, then the other frame measures the same acceleration. Isn't it great? Okay, now the separation of events. So let's say two events, A and B happens, and then the two frames measure it independently. So now let's talk about separation of events. Just give me a second. So yeah, so separation of events, and this is the important part, right? This is going to determine us the geometry. So separation of events, excuse my complacency, of events. So let's say there is one event happening here which is called the point A, and another event happening nearby which is B, and this one has coordinate TA, XA, YA and ZA. And then there is another event whose coordinates are TB, XB, YB and ZB. Okay, so then they are separated by space and time. So what is the separation in time? Okay, so the separation in time is going to be the separation in time. This is going to be t. So delta t in unprimed coordinate is going to be t b minus ta. I'm sorry, this is going to be equal to tb minus ta. And immediately you can see, because this can be the time is absolute in both frame, so tb prime and ta prime, is equal to ta prime, okay, and that is delta t prime. Great. Okay, now in space, right, it's detected or determined by Pythagorean formula, which is basically delta r equals what we have, delta, so delta square root of delta x squared, but let's say delta r squared. So delta x squared plus delta y squared plus delta z squared. Okay, so that is the formula we get from Pythagorean theorem. And of course delta x is xb minus xa whole square, and so on, right? But you notice if you substitute that, the relation, right, of xa and xb with xa prime and xb prime from this kind of relation, okay, what do you find? You find this x, this can be written as xb minus vtb, okay, and am I writing things correctly? Yeah. And then you have actually I don't have to, because minus xa minus plus vta. Well, just separate it. Actually, I don't need that, because it's special separation, right? So this is separated by, just give me a second, okay? So it's a geometric property, so both of them are going to measure the same difference. Distance between three-dimensional okay, so this is, what can I write here? That's what I'm thinking. So xb prime minus xa prime, that is not the same as, so xb prime is going to be xb minus x vtb, and but the time doesn't enter here. Okay. Let me think for it for a second. So actually, yeah, time doesn't enter here because we're okay. Yes. So as we're measuring the spatial distance, right? We're not doing it at different time. I'm sorry, this is wrong. So we're not doing that in different time. We're doing that at the same time. So basically, this is going to be xb prime minus xa prime, and so on. Correct? Because we are measuring the spatial distance. Excuse me for bringing time into it, but the time shouldn't come into here. So I have x prime squared plus delta y prime squared plus delta z prime squared, and that is going to be delta r squared, r prime squared. And the reason, so in this I'll have to write the reason here. So spatial distance, spatial difference must be measured independent of time. not independent, or I should say at the same time. At same time. Okay, so that ought to be the reason. Okay, so basically what I'm trying to say is that the space and time, they don't mix with each other. That's what the important part here. So I'm going to write in Newtonian mechanics, space and time don't mix, do not mix. Okay, that's the most important takeaway from here. Okay, so the geometry is this is the geometry of Newtonian mechanics. So Newtonian geometry is T delta T prime equals delta T, and delta R prime squared equals delta R squared. Okay, so that determines the Newtonian geometry. I hope this is clear. Let me check if there is any other question. Okay, I'm looking at the chat. Please let me know your question. I'm gonna move on, but I'll ask the question and I'll be answering that in a minute to the best of my ability. Okay, so let me go on to the next one. Please keep asking your question. Okay, so the next thing, we just talked about Newtonian geometry, right? So of course we will be going back to equation number 2, like this one, and then we'll be talking about Minkowski geometry, Einstein's geometry. Okay, and this is where the interesting distinction of special relativity starts to make, or the deviation it starts to make from our traditional knowledge of Newtonian geometry, even though what we are going to see is actually the more natural one, but it's not the more familiar one, because we do not operate at speeds that are closer to the speed of light. Okay, so there's a question. Okay, ask whatever question you have and I'll try to answer, if I know that thing. So the next point is, what color did I use there? I just want to be consistent. Sorry for this pedantic behavior, but this is special space-time geometry. Okay, space-time. Now it's not hyphenated. Space-time geometry of special relativity. By the way, if you're listening to this, you might also want to find out my previous live session, which is the prior to this one, where so this live session started right after where we ended the first live session. Okay, sorry for all the noises. So check that out, and of course the next live session will start where this one ends. So even if you miss it, you cannot hear it for the whole time right now, don't worry, everything has been saved for you and you'll find it in my channel. Is there any more question? Okay, so far not. So let's get into the space-time geometry. So in special relativity, Einstein abandons the idea of the absolute time. So Einstein says no absolute time. So time for you doesn't flow at the same rate as a time for me, even though we are in two different inertial frames. Okay, as long as there is a speed difference, as long as we're not in the same inertial frames, the rate at which the time flows is going to change. And instead, it is replaced by the constancy of the speed of light. So, replace no absolute time replaced it with the constancy of the speed of light. Okay, speed of light. And this is kind of bizarre if you really think about it. Okay, if you are moving with respect with my respect 5 meters per second ahead, let's say, so this is you, okay, you are moving, okay, let's say this is me and this is you, okay, so me, you, okay, and then you have the best friend she told you not to worry about, right? Just a little joke. And we are both running, but you are faster than I am, and you are running 5 meters per second faster than I am running. Okay, so I'm running at some speed, let's say v, and you're running at v plus 5 meters per second. And this guy, okay, so guy, he is running 5 meters per second faster than you. Okay, so we'll write it in here, 5 meters per second faster than you. So you are running, your speed is v plus 5 meters per second, and then he is running another 5 meters per second faster than you are running. So with respect to me, what I'm going to observe, right, is that he is running 10 meters per second faster than I am running. That's just simple the law of addition. Okay. Okay, so there is a question, where can I connect with you? I am a STEM major, and I believe you're a PhD in physics. Thank you for considering that. Unfortunately, I am not a PhD in physics. I am just a physics enthusiast. I have done a master's in physics, so honors and masters in physics. Where are you? And I hope I probably can. You can. Okay, that's a good question. I should have like a forum where you can join. So let me think about it. I'll then create a forum, probably through some social media, and then I'll be posting that on the next time. But thank you for trying to join. And probably I'll be joining PhD soon. So, but nevertheless, I'm just a student of this discipline. I myself am a teacher. I've been teaching for quite some time, but I haven't started my PhD yet. So that is my eventual goal. Hopefully that works out. But nevertheless, please stay with this channel, and I'll be posting my social media soon. Okay, so where you can join. Okay, so So this is the generic rule. Okay. Instead, let's say what Einstein says is, wait a second. If, let's say, so again, the similar scenario, but we are having a very high speed. So I'm moving at the at whatever speed, let's say c by 2. So my speed is half the speed of light, and you are moving. So again, this is you are moving at faster than me, but faster by what? Again, half the speed of light. So okay, so let's say no, let's not make that, let's make 1/3 by 1/3. And so if I shoot a light from here at a speed of light, what should you see? You should be able to see that the speed of light with respect to you has the speed, so v equals c minus c by 3. That's what you should notice, right? This is the expected speed of light for a Newtonian observer, because you're so used to Newtonian relativity, Newtonian observer, right? You're so used to it that you should be able to you'd be expecting the speed of light would be 2c over 3. But wrong, says Einstein. Einstein says no, this you will also, so you will also measure the speed of light to be c, exactly what I would measure. Okay, so basically the speed of light c is the same in all inertial frames. Okay, that is the Einstein's new postulate. Okay, so what does it say? The constancy of the speed of light in or across all inertial frame. Okay, so you see the speed of light to be c, and I see the speed of light to be c, and that's what Einstein replaces his postulate with. Okay, great. So now this is gonna give us our next set of relationships. So what is the set of relationship? So let's say again we have our standard configuration. I don't want to draw it again, so I'm just going to copy it, okay, if that's all right. So that's, I think, will do the job. Excuse me. Control copy, and then I'm gonna paste it here. Let's see. Okay, so that's the thing, and what we're going to do is that from when these two coincide, right? So when the standard configuration coincided, when S and S prime coincided, let's not write so many things. When S and S prime coincided at t equals t prime equals 0, okay, there is a flash in the origin. So there is a flash at the origin, flash of light, basically, at the origin. And then we keep going, and the question is, what do we see? Okay. Now, subsequently, when t, so subsequently means subsequently t equals so t is greater than 0 and so is t prime. Okay, so we are talking about the later instance. Okay, then the coordinate of the photon is going to be what? It's going to be according to the distance divided by time. Okay, so the photon's coordinate would satisfy in both frame. It will satisfy v square or c square equals delta r squares divided by time squares. I shouldn't say delta r square because the endpoint of the r is basically the origin, so delta r square and r square are going to be the same. So, and this is going to be r prime squared divided by t prime squared. Okay, from this we can see that c square t square minus r square, I'm sorry, this should be square, c square t square minus r square equal to 0. Can you agree on that? You just take it with this one and then c square t square equal to r square, and from that you get this. Okay, fair enough. So this is very simple. I'm just breaking it down in case you may haven't got it at the instant. Sometimes that happens, so I'll try to make it as convenient for you as possible. So I have c squared t prime square minus r prime square as well. Okay, so what does that entail then? So r prime square is basically x squared plus y squared plus z squared. Okay, can we agree on that? And we have c squared t squared, and this is equal to 0. And the same goes in here as well. C squared t prime squared minus x squared plus y squared plus z squared, everything inside the bracket, so that if you lift off the bracket, all the plus signs inside the bracket becomes a minus sign. Okay, now what we're going to do is to substitute this relationship. Where is my equation number 2? Here we're going to substitute these relationships into that set. So can I just copy it? I can just only copy this too. Okay, so let me just copy it and then try out the algebra. And this would be the last topic. I'll let it go, I promise. If you're watching right now, I usually do these things, these live sessions for an hour. So do that. Thank you for the subscription. Of course, on the next one, or in the comment section of this one, please also look there as well. I'll be posting some sort of forum where the followers can join, so I'll be keeping that in mind. Thank you for pointing that out there. So where do I paste it? Let me paste it here. Okay, so some bottom corner, like that. Okay, let me make it smaller as well, so that. Okay, great. So let us write first c squared t squared minus x squared, and then notice you have. Okay, we have y squared and z squared, right? But this is equal to c squared t prime squared minus x squared x prime squared minus y prime squared minus z prime squared. Okay, and now you basically cancel these two. So So this cancels y prime squared because y and y prime are the same, and then z squared cancels minus z prime squared because they are the same. So now we don't have a lot of things. We can just simply put things back in their order. So I have c squared t squared minus x squared. On the other hand, I have c squared instead of t squared. I have, what do I have? I have a squared, at plus bx whole squared, right? Minus, instead of x prime, I have a times x minus vt. So that whole squared. So this squared and that squared. Okay, so I've substituted that, and then what do I get? I get, if I have to simplify c squared, so I get c squared, I get a squared, t squared, excuse me for the sound, then I have 2a b t x, and then I have b squared x squared. Then I have minus a squared x squared minus 2vxt plus v squared t squared. Okay, so on the next one I have, what do I have? I have c squared t squared minus x squared. Okay, so this looks very complicated, but I promise that this is going to be much easier. So notice, what do I have here? I have c squared, and then I have t squared, right? So let's take everything that is the coefficient of t squared, and they have to be the same. And let's take everything that is the coefficient of x squared. Actually, the other way around. Let's take everything. I'll have to solve it like this. Okay. So this is a bit crooked. Sorry for the algebra. I know it's a bit boring, but let me just show it for the sake of completeness. This is a good exercise for me as well, so I'm being a little selfish. So I have c squared t squared minus x squared, right? So what do we have here? All the t squareds. So I have t squared. So everything that pertains to t squared. So where do I have it? C squared, a squared, and I have, there's a minus sign, there's a plus sign here, so minus minus v squared, a squared. Okay, so that's the coefficient of t squared. Now I have something like t times x plus tx. Okay, what are the coefficients? I have 2ab squared minus 2a squared. Actually, this is plus, right? Negative and negative make it positive. 2a squared v squared xt, that's been separated before, so I don't have to write anything else. And that's it. And what about x squared? Okay, so I'll take a minus x squared, so I'll have a squared minus c squared b squared. Okay, because notice this has a plus sign, so the two negative signs here and here will make it plus. I hope that algebra is correct, because otherwise we're gonna have much problem. So the first thing we notice that there is no corresponding tx term in here. Okay, So immediately what we notice is that twice ab c squared plus 2a squared v squared equals 0. Okay, what else do we have? We have so that's equation let's say star 1. Equation star 2, what does that say? That says that, let's take the coefficients of t squared. So I have c squared equals c squared a squared minus v squared a squared. Okay. And then finally I have a squared minus c squared b squared equals 1. Okay, so we have 3 equations. They must be consistent, otherwise we'll run into trouble. I really hope that they are consistent. So so what do we have? We have so this is equation number 3. Sorry for the handwriting. I'm a bit tired, so the handwriting had got the best of me. So I have so take the equation number 2. So number 2, from there I can take a squared times c squared minus v squared equals c squared. Okay, that's great, because then a squared equals c squared divided by c squared minus v squared. Okay, does it seem a little bit familiar to everyone? Because it seems to me, because I can now take c squared and divide the numerator and the denominator both with c squared. So I get 1 divided by 1 minus v squared divided by c squared. And if I try to take a, well, look at what I have got. I have got 1 over square root of 1 minus v squared divided by c squared. Does everybody know what this is called? This is denoted by gamma, and this is called the Lorentz factor. This is a staple Lorentz factor, and this is the staple of special relativity. We are going to see this gamma factor everywhere. Okay, so that's a great thing. Okay, so let's pick the next easiest thing from where I can now use. So a is now gamma, right? Let's take equation number 3. So from number 3, a squared minus c squared b squared equals 1. So from number 3, a squared minus c squared b squared equals 1. Is that correct? A squared minus c squared b squared equals 1. So, okay, I think that is correct. So I have gamma squared minus c squared b squared equals 1. Well, so then I have b squared c squared equals gamma squared minus 1. Okay, now I have to be careful here, because gamma squared, if you remember, is actually c squared divided by c squared minus b squared. So c squared divided by c squared minus v squared, and if there is a 1, I can take that into the fold, and this become minus c squared plus v squared. Well, what is that? That is simply v squared divided by c squared minus v squared. Okay? Now this is what I'm going to do. I'm going to write v squared equals v squared divided by c squared. Okay? And And so we have c squared minus v squared. Okay, and if we try to put it in terms of gamma, so yeah, if we try to put it in terms of gamma, what do we find? We find okay, let me just think about it for a bit. I mean, what I'm thinking about is I can divide everyone by c squared again, so this becomes c to the power 4, and this becomes 1 minus v squared divided by c squared, and then I have gamma squared v squared divided by c to the power 4. That's what I get. Okay, no problem. Now, for making things a little bit simpler, what I'm going to do is to define a little definition. So beta, this is what I'm going to define. Beta equals v divided by c. And so here gamma becomes 1 over square root of 1 minus beta squared. Once I have that, can I make b squared a little bit prettier? I think I can. So what I'm going to do is to write b equals gamma times v divided by c squared. And so I have beta, gamma times beta divided by c. Okay, great. I've simplified things by a lot. So a is gamma and b is that, and so if we substitute that in our relation, where is the relation? I did put it down here, didn't I? Yeah. So again, let me bring those up in here. Okay, so this implies what? This implies t prime equals gamma times t plus beta is gamma beta over c times x. Alright, now I'm gonna make it a bit prettier. I'm gonna multiply everyone by c. So I have ct prime equals gamma times ct, okay, and then plus did I put the plus or minus? Excuse me. So beta, I think I should have minus here. Actually, I should have put plus minus here, shouldn't I? Because the velocity could be in any direction. So there is a plus minus here, okay, that we'll have to address whether this is going to be the plus or this is going to be the minus. So I'm going to go there in a minute, but this should be our ansatz, beta times x. And then I have x prime equals gamma, because a is gamma, times x minus vt, right? But notice if beta is v divided by c, what I can do here, because I have a v here, I can, instead of v, I can write beta c. So that's what I'm gonna write, and you can ask me why, and if you just look at it, beta and then ct, and notice everywhere in these two equations t doesn't appear alone, t or t prime. Whenever time comes, it comes with c, and that's a good thing. Why that's a good thing? Because c times t is basically distance, isn't it? And or the unit of spatial coordinate, space. So now if you keep ct together at all times, then you can basically treat it as x, because notice in the expression of t there's a linear x, or t prime, there's a linear x, and it is sitting linear with t. So essentially x and ct, or space and time, are now interrelated. Okay, that is the wonder, that is the awesomeness of relativity. Okay, so so then I have to address this plus minus here. So what's happening here? So if we're thinking about like the standard configuration, right? The S prime is going forward, then this sign should be negative. This should be negative. Okay, not the positive, because we'll have to put that back into our original relation, which is in here. Okay, and it ought to be consistent, and it should also be consistent with the matter of the geometry as well. Okay, so if we are considering the geometry, then we ought to or we should put the negative sign here. But then the question of geometry is a nuanced thing, so this is where we should stop, and on the next session I'll be starting from here and clarify what this should be a negative sign. So unfortunately we have my allotted time was actually 1 hour. We have gone far beyond that, and on the next session we'll be starting from this. What I'm recognizing is that a stream in this time is much more convenient to everyone else, so that's what I'll probably do. I should do the live stream in the morning. Please find out the previous live stream that is on relativity, that is also saved here and published. So stay tuned, subscribe, and then